This project aims to demonstrate the conservation of energy by seeing how much energy was lost based on our roller coaster, where we will be doing our calculations, and to analyze the energy efficiency by seeing how much energy was lost and identifying what we can do to avoid any loss of energy.
So first is for the highest point of the track is 45.6 centimeters or 0.456 meters. For the second highest point is 16 centimeters or 0.16 meters. For the second highest, and for the loop is 26 centimeters or 0.26 meters above the surface.
This project aims to demonstrate the conservation of energy by seeing how much energy was lost based on our roller coaster, where we will be doing our calculations, and to analyze the energy efficiency by seeing how much energy was lost and identifying what we can do to avoid any loss of energy. Roller coaster, that means that the energy does not become lost but changes from one form to another. The sum of kinetic and potential energy, which is mechanical energy, of a closed space remains constant. That can be described algebraically by saying Ke plus Pe equals Me.
At the top of the roller coaster, or the highest point of the marble track, the marble has maximum potential energy, or PE, because of its height. The formula for the PE itself is mass times gravitational acceleration times height. And from my own data, or the track that we made, the mass of the marble is 1.8 gram or 0.0018 kilogram. For the height is 0.456 in meters, and for the gravitational acceleration is always 9.8 meter per second square. So using the formula of potential energy, we'll have the number of 0.00798 joules. At this point, kinetic energy is zero because the marble is not moving yet. But as it rolled down, the potential energy transformed into kinetic energy, which gave the marble its speed. By the time it reached point B, which is 16 centimeters or 0.16 meters, potential energy dropped to 0.0028 joules, while kinetic energy climbed into 0.00509 joules. This shows that energy isn't lost but it transformed, just as the law of conservation of energy predicts. There are several factors in our roller coaster design that affect energy transformations and the overall efficiency of the system. Here's how these factors come into play. First is the track height. The impact is that the height of the starting point determines the amount of gravitational potential energy at the start. A higher starting point gives the marble more energy to convert into kinetic energy as it moves, resulting in greater speed and momentum. In my experiment, I measured the height. The highest point is 0.45 meters or 450 or 45.6 centimeters, which directly influenced the marble's initial potential energy. Second is the friction between the marble and the track. The impact is that the friction converts some of the marble's mechanical energy into heat energy, reducing the total energy available for motion. The friction can be because of the unsmooth track caused by the tapes that was attached on the surface of the track. And to minimize them, I might need to choose other materials or make sure that I didn't attach the tape on top of the surface. And the third one is the track shape and curves. Uh, in the track shape and curves, we're talking about the loops, because the loops or the loop slopes may cause the marble to lose contact with the track if not designed correctly, or it could disrupt the energy transformation. And last is the air resistance. Air resistance increase with speed and surface area. Though minimal in our marble experiment, it becomes significant in larger roller coaster designs, reducing efficiency by converting kinetic energy into heat. So that are the factors that might cause our uh, roller coaster design to not able to show the efficiency in our system properly. Well, that's it for the explanation from us. Thank you so much for watching our video. Bye.